Anyhow, we're going to go for another technical session this morning, and a lot about salt caverns and also about monitoring, which will be finalized with a discussion session moderated by Diane. But first of all, I would like to welcome our first speaker, and I have to pick up my glasses, sorry, which is Dr. Benoit Brouard, and he holds a Master of Science degree for Arts and Métiers in France, and he holds also a PhD in rock mechanics from the École Polytechnique in France. He has 30 years of experience in rock mechanics with particular experience in salt caverns. Benoit Brouard founded Brouard Consulting in 1999. He has co-authored over 100 technical and journal articles on salt cavern behavior. Benoit was president of the Salt Solution Mine Research Institute in 2015. Benoit, please.
Thank you, Serge. Can you hear me? Good? Okay. Good morning, everybody. Thank you for the kind invitation. I'm a guy from the salt caverns. I know that most of you are in the field of porous media. That's why my presentation today is more kind of overview of the physical phenomena involved in salt cavern. In fact, it's a kind of a teamwork. We created a kind of consortium a few years ago, which is called CCC, made of different companies, mainly spin-off of universities. And the story started a few years ago, excuse me, because of these two very famous professors. Pierre Berès was a kind of world-class expert, maybe the best expert ever in the rock mechanics, mechanics of salt and everything. And Janos Roy here in the Netherlands and in Germany was very famous in the world of microscale. And both decided to create a consortium, it was 3 or 4 years ago, to look at the problem of cavern abandonment here in the Netherlands. And most of the results I will present today comes from work done through the years by these two persons. First, I'm not sure to have the right version of my presentation here. I have to check because I think there is not exactly the right one. Just let's check 1 second.
Sure.
Yeah, I think it's not the one I copied this morning. I have my... It makes a slight difference, but
No problem.
if we have 1 minute, it's better.
Of course.
Because I made some change in my presentation during the night. Because looking at what you presented yesterday, I think that it would be good to make some new slides to just comment on what I've seen yesterday. Yeah, it looks good, this one. Yeah, this is the right one. You just to open it, that's fine. So I restart from scratch. So you are already aware. So I said that we started looking at cavern abandonment. This is we founded this team to respond to requests from proposal from the SODM, the State Supervision of Mine of the Netherlands, looking at the cavern abandonment. Because for any new project, the big issue here in the Netherlands is to get a permit. If you would like to get a permit to create a cavern, to store hydrogen or what you want, you need to look at the problem of cavern abandonment. And this is a really big issue. So we had made this report called CAM17 with all the team. And more recently, we started to work directly for the Ministry of Economics regarding the storage of hydrogen. So with the same team, but adding a new company called Pandera, which look at the risk analysis. And it's because of the two Guyans recently, they just passed away, and it's a big loss for the community. So I'm going back to my presentation. So if we look at the rock salt as a host rock, as you will see, there are many thermo-hydromechanical properties that are involved with host rock, and they are involved at different time scale and also length scale. And salt is very heterogeneous. It's composed of different type of salt, different impurities, and the behavior of salt is very complicated. It flows, bends, expands, shrinks, breaks, dissolves, and so on. Many different processes. And to understand all these processes, it's very important. Understanding these processes is very important if you would like to design a cavern, you would like to know how to operate a cavern, and also how to abandon a cavern. And with our team, which is now called H2CCC, I don't know how we should pronounce this, we have a kind of workflow. We call it Sustainable Salt Cavern Life Cycles. And all our studies start with what we call a size-specific initial state determining this, which is called Ist-Zustand. The workflow is as follows. We start from a site selection somewhere. This is a map from the Netherlands. Then there are some drilling, coring, and from the course you can upscale, interpret what is geology at the scale of the salt dome, for instance. You can also look at the microstructures, looking, for instance, at the grain sizes. And we need each time to perform creep tests. I will show you that there are different types of creep tests that can be performed. And if you have creep tests, you have data. You have to analyze this data. It's not always very obvious. And at the end of the day, when you have all the data needed, we are able to start performing numerical computation. And this is my field of expertise, so this will be the main topic of my presentation today. You are already aware that we can do a lot of things with salt caverns. There are already existing caverns for storing hydrogen, for storing compressed air. And there are many ongoing projects everywhere worldwide now. And I already told you that salt caverns, the modeling of salt caverns is quite complex. It's supposed to both consider the thermodynamics of the cavern, inside the cavern, but also the rock mechanics, both. And you will see that it's very important to couple both phenomena. If you would like to analyze the cavern, I made my PhD on salt caverns, on the behavior of salt caverns a long time ago. There are many physical phenomena. Today I will be focused on the two first one, creep closure, thermodynamics, but you have to be aware that there are many different type of phenomena that can make, for instance, the pressure in a cavern change. For instance, the atmospheric pressure variation, even if the cavern is very deep, you can feel it in the cavern. And also earth tides, for instance. Some information about the rock mechanics. You have to be aware that salt is probably one of the most complex materials you can find. There were 10 international conferences dedicated only to the mechanical behavior of salt, starting in the early 80s. Last conference was in Utrecht, here in the Netherlands last year, and the next one will be in the US probably next year. It's a very complicated topic. There was hundreds, maybe thousands of people looking at the mechanical behavior of salt because not of the caverns, but because of the nuclear waste disposal, especially in Germany and in the US. To summarize the behavior of salt in a few words, we can say that the rock salt behavior is highly nonlinear. It is elastic ductile when considering short compression test, and it's elastic fragile when tensile tests are unconsidered. If you just keep something in mind, you have to consider that rock salt, is a liquid. It's a very viscous liquid, but it's a liquid, even if it's a rock. Important fact that all caverns shrinks. All caverns. It means that on the long term, all the caverns will disappear someday. Maybe in 10,000 years, you don't know, but they will all disappear because of the creep closure, because salt is a liquid. There are some examples here from different places worldwide. You have seen this type of slide yesterday, the different regime of the strain as a function of time when you perform a creep test. I don't want to describe too much about this. Just let's focus on the second part, what we call steady state creep or secondary creep. In fact, there are two different mechanisms for this steady state creep. The most famous is a nonlinear part. This is what used to be measured at the lab. You just measure the strain rate, or the strain as a function of time, and you calculate the strain rate, and you have something which is non-linear. The problem is that you can only make a measurement for a deviatoric stress which is larger, like let's say 4, 5 MPa, not less. And when you would like to compute the behavior of a salt cavern, you need to take into account a much larger volume of salt around the cavern, where the deviatoric stress is much less than 5 MPa. So that's why for a long time, it started here in the Netherlands by Janos Roy and Chris Spires. They have found that when we look at the micro scales, the behavior of salt at very low deviatoric stress should be linear. And this is an idea that they published in Science in '86. And it was just an idea, but nobody really understood or believed this at that time. And at the end of the 90s, with Pierre Beres, we started to perform testing in a mine at this low deviatoric stress. It was a way to check this assumption made by Janos and Chris. And it was observed that this prognosis was correct. When we consider a small deviatoric stress, we have a linear relationship between the strain rate and the deviatoric stress. And so we have two mechanisms that are called dislocation creep for the nonlinear process and the pressure solution creep for the low deviatoric stresses. When we look at, let's say, macroscopic law for modeling salt caverns, there are, in the world, 3 main types of laws that are considered. It depends on where the creep tests were performed in the lab. For instance, if you ask to the School of Mine in France to perform creep tests, they will provide you with a set of parameters for the so-called Lemaitre law. So it's a very simple law here on the left. If it's in Germany, you will have the Lubitu law, and in the US, it will be Munson-Dawson law. I don't have time to describe this, but you just have to look at the component of this law. Lemaitre law is purely transient. There is no steady state in this law, and the two others are both a component of transient and steady state. Important fact to remember that when you would like to model the behavior of salt, you at least have to consider 3 mechanisms: the steady state, the transient, and the pressure solution. Steady state, you can get it from the lab, and also it could be calibrated from field test. The transient also can be calculated from a lab test, and this is something which is very important for gas cavern like hydrogen cavern. And pressure solution, probably you can only get it from tests performed in a mine. Important, this slide, I've seen a few reports, recent reports made in Europe that make some calculation with hydrogen caverns, cycling, fast cycling, blah, 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 but without considering transient creep. There was only steady state creep and pressure solution creep. So only steady state, no transient mechanism in this. And I just made a very simple calculation of hydrogen cavern with a 3 seasonal cycle like this, and comparing with and without transient creep. And as you can see, on the bottom left, you have the loss of volume of the cavern. Bottom right, this is a volume loss rate. You see there's a big difference. So it means that you have to include a transient mechanism in your creep law, and it's not always not very obvious because the implementation in the finite element code could be quite complicated. Something which is quite uncommon with the rock, this is what we call reverse creep. This is a kind of special feature of rock salt. If you consider, for instance, a salt sample and you apply a load for a while, sigma 1 here, and just suddenly you remove some load. You keep some load on the sample, but you remove some part of it, and you can observe an increase of the height of the sample. It means that the sample is able to provide some energy back to the system, which is something which is a bit special. And this is something that Pierre Beres was working on before he passed away, and he determined this modification of the Munson-Dawson law that takes into account this reverse creep. And he spent a lot of time on this because he would like to get a formulation that is thermodynamically consistent. But this has not been tested yet. Some information about the thermodynamics. Just you have to remember that initially when you create a cavern, you inject some water that comes from the ground, and most of times the temperature of the water is less than the temperature of the rock. So it means that at the end of the mining, the temperature of the brine in the cavern is much less than the rock, and so you have some heating of the brine on the long term. And after the leaching, before the first gas filling, you have some resorption of the difference in temperature. It's mainly due to the convection in the caverns. There are convection cells. This is an example of a measurement that was made in a cavern called Easy 53. This cavern is very famous. There is another presentation, I think, today about the Hipster project. And the first pilot we have in France, this is with this cavern. This cavern was leached out in '82. And you can see some measurements that were made in this cavern over a few months. And you see there is a slow increase of the temperature in the cavern. This heating process could be extremely slow because it depends on the size of the cavern. This is a very small cavern, 8,000 cubic meter. In the real world, if the cavern is 1 million or more cubic meter, it takes decades or centuries to equilibrate, because caverns are really huge objects. I told you about the free convection. So in any cavern, you have convection, natural free convection, because you have a gradient of temperature in the soil, so you cannot avoid to have convections, and the convection cells depend on the cavern shape and can be calculated. Just from an example of a type of typical cavern we can have here in salt domes in the Netherlands, in Germany, something which is a kind of cylindrical cavern, could be very deep. You know that the deepest you go, the highest the temperatures you get, and that's good for microbes, because you know that we can get microbes at maybe, I don't know, 60, 70, 80 Celsius, but when you go deeper, if it's deeper, the microbes can disappear, so it's good to have a kind of elongated cavern with a bottom quite deep, because you have probably less risk with the microbes. However, I made this slide yesterday. If you look at on the unleachables, how do you pronounce? I don't know how you do pronounce. Maybe we try to get a new word. So you have sulfates in this at the bottom of the cavern. So you can think that sulfates are protected from the hydrogen because you can have a kind of large amount of brine between the two. The problem is with the convection, because you have convection cells in the brine, so probably you cannot avoid to have some mixtures in the sump, and so the process cannot be avoided. Yeah. The best way is probably, even if the brine is saturated, you should have a quite large temperature. It's copyrighted. Yeah, sorry, he made it during the night. Sorry, it's too late. Something that's also interesting, this is a role of water vapor. In many cases, the cavern gas at rest is saturated with vapor, blah, blah, blah. And depending on the change of the pressure, temperature in the cavern, the vapor pressure can be saturated, oversaturated, undersaturated, blah, blah, blah. We have some measurement. What is good with salt caverns that we can measure many things. It's a closed system, and we are able to measure the variable. For instance, here it's a measurement made of the temperature of the brine in the sump, and it has been determined that when the cavern is submitted to many frequent cycles, the temperature of the brine is decreasing. I have 5 minutes for 50 slides, and don't worry. And so you have just to know that there is a different process which is asymmetrical. When you consider gas withdrawal or gas injection, you can have some oversaturation, undersaturation, and so you can have some rain in the cavern, even some snow sometimes, and that's the process that can be computed, but quite complicated. Energy balance, I don't want to describe this. Just remember that everything is coupled. In this equation, you have the volume of the cavern that comes from the rock mechanics, and so rock mechanics, thermodynamics, they are all coupled together. When you look at the cavern stability, it's complicated. When you have the swings of the temperature, you trigger some thermo-elastic stresses, and you can get some frac, to be simple. 1 Celsius variation of the temperature, 1 MPa additional stresses, so you can get a frac. Also, when you go down at the minimum pressure, you can get some dilation. And dilation, it was presented yesterday. This is a kind of microfracturing, increase of permeability of salt. I have no time to describe this. Just to let you know that there is a big software that we are developing for decades now. It's more than 1 million lines of code just for the pre and post processing, plus I don't know how many lines for the finite element code, and so on. And it helps us to design the caverns and at different time scale. Just a few slides to show it looks like. You see the 3D version. This is, for instance, this is zone vending salt caverns with the actual shapes of the caverns. I show you an example of a 2D simulation of it's a hydrogen cavern with a seasonal cycling, 10 years of cycling like this. You can calculate the loss of volume and the increase of the brine and hydrogen temperature, all the calculate all the developed energies. And also, we look at the cavern stability. This is an example. We look what's going on at the minimum pressure, the effective stress contours. You see all these magenta zones here. This is where you probably get some kind of hydrofrac. Even if you are at a low pressure, you can get hydrofrac. This is a slide that comes from our colleague, Herminio, that presented the boundary between compressibility and dilatancy in a space with shear stress as a function of the mean stress. And I was just to let you know that things are very complicated. For example, I consider what's going on at this location at the cavern wall, which is the red dots here, and what's going on over time at this location when you just cycling, sinusoidal cycling, very simple. What you expect? Maybe you can expect something also very simple like this, because you are just repeating the cycle. But in the real world, it's something much complicated. It's something, you see? This is what we call the bumblebee flight. You see, you can hear the bumblebee. It means because the stresses is always moving in the space of the stresses like this. Nothing is stable. In a cavern is something that is always alive, and even at a given point, it's always changing the state of stress. Something which worst case scenario for a gas cavern, this is what we call the blowout. Here are two examples of blowouts from a natural gas cavern, one from the US on the left, one from Canada on the right. This is something which is very surprising, and you cannot stop. You have to wait for the end of the blowout, and all the gas is lost. And the modeling of a blowout is something quite complicated because you cannot determine in advance what will be the duration of the blowout. This is a result of the coupled computations. And the modeling is complex because there is a kind of subsiding flow at the wellhead. For instance, hydrogen is escaping from the wellhead at the velocity of sound. And the velocity of sound in hydrogen is very high, in the order of 1,200 meters per second. This is the velocity at the wellhead. And so there are two different regimes during the blowout. The first one is called the shock flow, and the second one is called the normal flow. I don't have time to explain this, but this is something that could be computed, but not so obvious. This is an example of computation of a blowout from a nitrogen cavern. You have the gas velocity at the top left. I have no time, so look maybe on the right on the temperature. Top right, this is the temperature at the wellhead, and you can see that the minimum temperature you get at the wellhead is here, minus 56 Celsius, so it's extremely cold as a minimum. And even in the cavern, you have a minimum of minus 14 at the bottom right here, and so you get some damage during the blowout because of the tensile stresses you create because of the large cooling of the hydrogen. And in some cases, because you are going very fast to the low pressure and low temperature, you can go directly from a gaseous form of the water in the hydrogen directly to a solid form. So in that case, it's snowing in the cavern, and this is what happens in Texas during the Moss Bluff blowout. It was in August in Texas, and it was snowing. That was the first time, maybe the last time. Yeah. And so here are my conclusions. I'm very late, sorry. So remember that for the modeling of salt caverns, it's complicated, but we have already the tools for that, and it's important to have a couple modeling between thermodynamics and rock mechanics. And you have to take into account all the mechanism, including the transient creep. And you can get some damage, dilation, tensile effective stress that can create fracture. All this can be calculated. Just remember that for in the real world, the salt is different from one place to another, so you have to perform a case-by-case study for all new projects. And if you have to calibrate your model using data from the field and not from the lab. I'm always fighting to promote the idea of measuring things on the wellheads in the caverns that you can do with caverns, not with porous media. And it's a good way to calibrate everything. So that's it. Thank you.
Thank you very much. Thank you very much. Great presentation. I learned a lot.
You.
Again.
Really?
So, yes.
No.
And I don't know if there's any questions from the room.
The snow in Texas was also not too bad.
See one above. Giovanni?
Giovanni is there. And
I let Hardy do the walking.
Only two. So the first day we were asking about what it would be important to study, and one of the questions was how the crack would propagate in soil. Was saying no, it's not important. From your presentation, it might be important. And the second question is, what do you think about the sigma 2 effect on the model, because it's not been accounted for? The intermediate stress. You assume that you always have basically a sigma 1 and sigma 2 and sigma 3 are the same in your model. But the boundary condition of your soil dome are not that one. So just your comments.
Okay, so first question about the fracturation. Of course, this is a big problem, and there is one PhD started probably in September in France on this topic, just to look at the onset of a fracture, the propagation of a fractures, everything like this. This is a hot topic that there will be a PhD. And your second question will on the state of stress. That's why we are working with a company which is called Smart Tectonics. It's a spin-off from the Mainz University in Germany. And their specialty is to look at the stresses in the soil dome, at the scale of the soil domes, in idea to provide us with what they call Ist-Zustand. This is, let's say, the stress field everywhere in the dome and outside the dome. That, of course, is not isotropic. So we have all the components of the stresses that can be input as a starting point when for the creation of the cavern. Okay. That's why we have a team, because we have to look at different scales, and it's for the stresses you are talking about, it's good to have a view on the dome scale.
There are some online questions, we do maybe quick. They said about the temperature variation.
Yeah?
Would it be higher or lower for hydrogen?
I know that some people pretend the first option and some other people the second option. I'm not sure. I'm not sure. It depends. If you have to consider the water content in the hydrogen and everything, and such, I don't want to provide you with a very,
sure.
You see,
absolutely.
Case by case study. Remember, case by case.
Every patient is different.
Thank you. It was a really interesting presentation. I'm interested to know more about the blowouts and what the causes were for those.
So. In the literature, there's only 2 examples, and the last one from Canada, we just hear about this year, maybe or last year, and it occurs maybe 5 years ago. Or so maybe there are others, but it's really kept secret. The idea is that there is some failure somewhere done all. In the case of the Moss Bluff blowout, it was a kind of overfilling. The inner string, the cavern was operated by injecting or withdrawing brine and keeping the pressure almost constant in the natural gas. And so they were injecting natural gas, and probably the inner string filled with brine was damaged somewhere. and it just there was some natural gas coming inside the inner string filled with brine, going very fast to the surface, and there was safety valves there, which is not at the right location, and it was not effective. So the wellhead just exploded and like this.
Yeah.
It's always a mistake of the completion of. This is something that can be mitigated, I guess.
Very quick question, very quick answer.
In the plot where you showed the kind of stress distributions due to a low pressure condition, and it was quite a complex cavern profile, and it looked like there was kind of quite extreme, like different stresses in the lining.
Yeah.
And I'm assuming that might result in areas where there may be failure in some locations, but in other locations it's okay. Are there cases where you have failure within the cavern, but it's acceptable? And how would you determine how much failure would be acceptable in a cavern lining?
It's difficult to quantify everything. What we used to do is only to make some post-processing to determine the zone, the extent of the zone when you get damage. But it's almost impossible, I think, to just calculate what will be the ongoing damage, because in the literature you can find some laws with some damage components in the law, blah, 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 but you need parameters for this, and there is almost no way to get these parameters from the field. You can do something on the lab, get some parameters from a given sample, but it's very difficult to extrapolate at the scale of the cavern. So what we do is just calculate let's say, the extent of the damage zone.
Let's thank Benoit one more time. I
Yes.
have plenty of questions, but in coffee break.